Hi guys, today we're going to be looking at a topic which should be reviewed to you, solving and graphing inequalities. So we have four major inequality symbols. They are less than, that you see up here. Hold on one second. Okay. We have less than, greater than, less than or equal to, and greater than or equal to. So some common inequality phrases that you'll see are P is at least 25. So that would look like this. P is at least greater than or equal to 25. Okay, and you could pause the video and see if you can translate each of the following up through example 4. G is no more than 8 would be G is less than or equal to 8. Example 3, N is no less than 30. N is greater than or equal to 30. And example 4, A is at most 5. A is less than or equal to 15, not 5, 15. Inequalities, if the variable is not isolated, then we solve them like equations. So if you look at example 5, I have 2x minus 12 is greater than or equal to negative 6. What I'm going to do is I'm going to isolate the x. So I'm going to treat it just like an equation. I'm going to add 12 to both sides. I have 2x is greater than or equal to 6, and then divide both sides by 3. This is saying that x can be any number greater than or equal to 3. This is our solution as an inequality, or solution set, I should say, because it's lots of solutions. It's 3 and any number bigger than 3, including decimals. So there are infinitely many solutions to this, but only solutions that are greater than or equal to 3. And these get graphed. So you go to 3 on the number line, and what we do is we put a colored in circle to show that 3 is included as a solution, and then we shade to the right. So this is showing that x can be any number that you see in the shaded area from 3 on to the right. All right, take a look at example 6. In this one, to isolate x, I would add 6 to both sides. Subtract 6 from both sides. I would have negative 5x is less than or equal to 20, and I would divide both sides by negative 5. Now we have a rule for inequalities, and that is when you divide by a negative on both sides or multiply by a negative on both sides, you have to flip this inequality symbol. And it becomes x is greater than or equal to negative 4. That's your solution set, and that gets graphed. Negative 4, it has an equal symbol. So you color it in and you shade to the right, greater than or equal to. Now, if these did not have an equal sign, if it was just x is greater than negative 4, then your circle would be open and it would still shade to the right. So that says x is greater than negative 4, not including the negative 4 open circle. The reason why we flip this when we're dividing by a negative or multiply by a negative is because if you have an inequality statement like 4 is less than 10, which is true, if you multiply by a positive number, any positive number, the left side will still be smaller than the right side, like 8 is greater than 20. But if you multiply both sides by a negative number, let's say you multiplied by negative 2, then it becomes negative 8 and negative 20, and negative 8 is not less than negative 20. In fact, negative 8 is greater than negative 20. So that always happens whenever you multiply by a negative number, and that's why we flip the inequality symbol. So just looking at examples 7 through 10, you should be able to take a look through to see and predict, would you have to switch that sign? Would you have to flip that inequality symbol if you were to solve? So without solving them, if you look at example 7, mentally you just go through and say, well, I would add 3. So no, I would not have to switch the inequality symbol. I wouldn't have to flip it. In example 8, I would have to divide both sides by 2. So dividing by 2, even though the 24 is negative, that doesn't get you to flip the inequality symbol or switch it. They're using the word switch because you're dividing by a positive number. It doesn't matter that there was already a negative number there. So no, you would not switch the inequality symbol. In example 9, yes, because you would have to divide both sides by negative 3. In example 10, yes, because you would have to multiply both sides by negative 4 to isolate x. So again, it only applies to multiplication and division by a negative number. Another important thing when you're working with inequalities is that you should always rewrite the inequality so that the x is on the left side. So if you see an inequality written like this, you want to have the x term on your left side. So if you rewrite it, 4x minus 2, now we're reading it backwards. You're reading it this way, is greater than negative 14. So make sure that you switch that symbol to reflect that you're reading it backwards. And now isolating x it's better this way, because then you read it like your answer is x is greater than so-and-so, as opposed to like 20 is less than x. That doesn't make sense. So we like to read it with the x first. 4x is greater than negative 12, divide by 4, x is greater than negative 3. Right? You wouldn't want to see negative 3 is less than x, because that doesn't really make sense. But x, some number, is a number bigger than negative 3. So I'm going to take negative 3. This time I'm going to put an open circle because there's no equal sign, and it's greater, so it's to the right. Any number to the right of negative 3, but not including negative 3. All right, we're going to work on identifying solutions. So if you're given an inequality, like in example 12, and they say circle all the possible solutions to the inequality, what you want to do is you want to first try to solve that inequality. And notice here that the x is on the right. So maybe you guys can pause the video and solve that inequality yourself. I'm going to rewrite this as 3x minus 1 is less than negative 25. And then I'm going to add 1. I get 3x is less than negative 24, and divide by 3. X is less than negative 8. So I want to circle all the possible solutions to this. I am only going to circle negative 12 and negative 35, because this is saying that x is a number that is smaller than negative 8, that is less than negative 8, not actually equal to negative 8. So negative 8 is not a solution because it's equal to negative 8. Negative 5 is not, because it's bigger than negative 8. 0 is not, because it's bigger than negative 8. All right, so the only two are negative 12 and negative 35. All right, and then we're going to look at something called interval notation. And interval notation is something that's brand new to you. Oops, I meant to use the highlighter there. Interval notation is something that's brand new to you. It's another way to express a solution set. So if you look at example 13, we have x is greater than negative 5. That solution set we can graph. We have, if you have a number line, here's negative 5, negative 6, negative 4. X is greater than negative 5 looks like this. It's any number bigger than negative 5, but not equal to it. In interval notation, what we do is we say that x can be any number from negative 5 all the way till the biggest number ever, which is the number. It's not really a number, but it's the concept of infinity. So we put a comma between them, and this says x can be any number from negative 5 all the way to the right to infinity. And I put parentheses around them. Parentheses show that you're not including that value. So we're not including negative 5 because it has an open circle, so we put parentheses around it. And we're not including infinity because infinity is not an actual number. Infinity is a concept. You can't actually ever include infinity. Okay, now if you look next to this, to example 14, I made it almost identical. It's x is greater than or equal to negative 5. So on my graph, I would see the same thing, only I would see that negative 5 is colored in to say that x could actually be negative 5. Right? So in interval notation, my value of x could be any number from negative 5 all the way to infinity, but this time I want to say that I'm including negative 5. So what I do is I put a bracket, I'll refer to it as a hard bracket, around the negative 5, and this shows that you are including negative 5. Infinity still can never be included, so that one gets parentheses. So you use one hard bracket on one side and parentheses on the other side. All right, now if we look at less than, so example 15, going on to example 15, says x is less than negative 5. So here's negative 5, again, negative 6 and negative 4. If x is less than negative 5 on a graph, it's not equal, open circle, but it's shaded to the left because that's where numbers that are less than negative 5 are. In interval notation, what we say is we say any number could be from, and we like to go from left to right on interval notation. Okay, so from the smallest number ever all the way up to negative 5. right? So on the number line, my eye is traveling from the smallest number ever, which is here, all the way up to -5, but not including -5. So the way I show that is I write the smallest number ever is -infinity. It's the opposite of positive infinity, all the way to comma -5. Not including -5, parentheses, not including -infinity, because it's not a real number, parentheses. Okay, and on the example 16, I have similar example, but I have less than or equal to -5. So less than or equal to -5 is just going to be colored in. And I have an interval notation. X could be any number. Again, I'm traveling from left to right. So from -infinity all the way up to +5. Including, excuse me, to -5, including -5. So again, from left, oops, got a pencil. From left to right is how we express interval notation. So from -infinity all the way up to -5. Those are all possible values of x. This time I want to include -5, so I put a hard bracket. But I don't want to include a -infinity, so I put parentheses on it. All right, guys, we're going to stop there, and we will continue with this on Monday. Okay, have a good weekend.